Hey, today we're going to look at some truly amazing consequences of some of the things that we've learned recently about power series. And we'll start by reminding ourselves of the Maclaurin series that we found for the three functions e to the x, sine of x, and cosine of x. All three of them converge for all real numbers. Here they are. And I want to come up with a power series representation for e to the ix, where I is the usual square root of -1. So in particular, I squared is -1. And to do that, we simply replace the x in the power series for e to the x with the continuous function ix, and we get this series here. And there's a lot of simplifying we can do. For example, ix squared, which we have right here, is ix times ix, or I squared times x squared, and I squared is -1. And similarly, ix cubed is I cubed times x cubed, and I cubed is I squared times I, and I squared is -1, and so we have that I cubed is -I. And ultimately, we're going to need all the different powers of I to the fourth, -1 times -1 is 1, which means that I to the fifth is 1 times I, or I, and it repeats that way, so that I to the sixth is -1, I to the seventh is -I, etc., etc. So that when we simplify our expression for e to the ix, we get this expression here. E to the ix is 1 plus ix minus x squared over 2 minus ix cubed over 3 factorial plus x to the fourth over 4 factorial, etc., as you see here. And if you look at this power series closely, you can see the series for the cosine of x sort of lurking in the middle of it. A cosine of x, 1 minus x squared over 2 plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial, etc. And so we can remove those terms and replace them with the cosine of x, and that leaves us with e to the ix is the cosine of x plus all the remaining terms, I times x minus I times x cubed over 3 factorial plus I times x to the fifth over 5 factorial, and on and on and on like that. And if you notice, all of these remaining terms have a factor of I in them. And factoring that out, we're left with e to the ix is the cosine of x plus I times x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial, etc. And this series here, that's just the power series for the sine of x, which gives us this amazing result that e to the ix is equal to the cosine of x plus I times the sine of x. And this little beauty is known as Euler's formula after Leonhard Euler. And conceptually, what it's telling us is that, at least in the realm of the complex numbers, the exponential function is all wrapped up with the trigonometric functions. In terms of the real numbers, it doesn't seem like the exponential function should have anything at all to do with the cosine and the sine or any other trigonometric functions. And yet, if you go up to the larger set of complex numbers, of which the real numbers are a subset, then it turns out that e to some power, the ix power in this case, it really is simply a function of the cosine and the sine in some strange and mysterious way. And here we have perhaps the most famous example of applying Euler's formula. Let the number x be equal to pi. Then Euler's formula tells us that e to the I pi is equal to the cosine of pi plus I times the sine of pi. And we know the cosine of pi and the sine of pi. The cosine of pi is -1 and the sine of pi is 0. And so simplifying, this gives us that e to the I pi is equal to -1. Let's take a moment and see if we can appreciate how shocking and beautiful and amazing and strange this is. This is what it's saying. Take the number e, 2.718 something or other. I can understand what it means to raise it to the pi power. I mean, pi is some number bigger than 3. I certainly understand what e cubed would mean. What is e to the 3.1? Well, that's e to the 31 tenths, or the 10th root of e to the 31, so I can understand what that means. What's e to the 3.14? Well, that's e to the 314 hundredths, or the 100th root of e to the 314. I mean, that might be unpleasant to compute, but I at least understand what it means. And so e to the pi, you could keep going in that way and sort of with a limiting process understand what e to the pi means. But e to the I pi is e to the pi raised to the I power, just by the properties of exponents. And how do you raise anything to the I power? That part doesn't make any sense to me anyway. I is the square root of -1. I wouldn't know how to start raising something to the I power. And yet Euler's formula tells us that when you take e to the I pi, or when you take e to the pi and raise it to the I power, you get not some crazy, bizarre, strange number that you would never have thought of before, but simply -1. I hate to keep using the same adjectives, but amazing, shocking, certainly mysterious. And just for entertainment, this little equation, e to the I pi equals -1, is often rewritten as e to the I pi plus 1 equals 0. And the reason that people like to write it that way is because it can be argued that this is an equation that relates the 5 most important constants in mathematics. 0, the additive identity; 1, the multiplicative identity; e, incredibly important in calculus; pi, the ratio of the circumference of a circle to its diameter; and I, the imaginary unit, the square root of -1. This little beauty tells us that they are all related in precisely this way. Anyway, that's Euler's formula. It's worth appreciating how it sort of unavoidably comes up just from the work that we've been doing all along, slowly, step by step, to get where we are now with power series. No step along the way, starting with when you looked at limits at the beginning of Calc 1, nothing was mysterious or strange, and yet you put it all together, in little increments, and it all comes out to this one bizarre, sort of mind-blowing result that I don't understand, and maybe you do, but if you do, please explain it to me. But it's true. No way around it. It's true. You have to accept all the steps that got us there, and so it's Euler's formula. Gotta love it. There's no homework on it. It's there for entertainment. More than that, it's sort of the culmination of 2 semesters worth of hard work in calculus, like the candy at the end. So enjoy Euler's formula, enjoy not having any homework, and I look forward to seeing you in class.